Hi, in this fourth video on managing Microsoft SQL Server memory, I'm going to start talking about the buffer pool, the memory clerks, and how all of these play a role in allocating memory to SQL Server during query execution. I'm also going to be trying to go ahead and relate this example in a way that you might be able to understand without bringing all the technical complexities that are associated with memory management in Microsoft SQL Server. To that end, I'll be comparing how memory is managed in SQL Server to the functioning or the way that a prison would have been managed. A prison obviously is a jail where people are getting stored. So people in this case would be considered the data pages, and the prison or the memory clerks would be considered the cell blocks in the prison. We'll get into that in detail later on. Also, in this particular video, I'll be talking about how the memory management is actually handled in SQL Server, specifically with a focus on how the query execution resizes the different memory clerks that we have available, and how SQL Server prioritizes which memory clerk needs to shrink or grow depending on what query or what the query is doing. So let's get started and dive right in. So now let's talk about how memory in SQL Server is very similar to how a prison works. To understand this, I'm first going to show you a prison and try to give you a broad idea about what a prison would look like. And then we're going to see how that maps pretty much similarly to what you would see in memory in SQL Server. I admit this is not a perfect example, but there are a lot of similarities. So I'm assuming that this will help you understand how SQL Server would work typically. And that information will then lay the foundation for further discussions. So I'm going to show you Tihar jail in India. Now this is basically the compound of the jail, and as you can see here, it's a pretty large complex. But what you'll understand here is that it's not one homogeneous block. You'll actually see that there are some significant demarcations as far as the memory is concerned. So if you look over here, everything between these two roads is the jail itself. So you'll see that we have this compound here, right? All this over here. This is basically the main jail complex. You can see that they've got a nice big boundary wall around it, but even these portions are actually part of the jail itself. So this is, I think, the police quarters where the police basically stay. So they don't stay inside the prison, they stay outside it with their families and stuff. But the basic idea here is this is how the jail looks like. Now, if you've ever been to jail, which I'm not suggesting you should, but you'll find that there are a lot of similarities. If you go to any real big jail, you'll find that there's a main cell block where most of the criminals are kept. You'll also find there is a separate cell block for women. There's a canteen, there's a workshop, there's a administrative block. You'll also find that there's usually a cell block for hardened criminals. So it's not like a prison is just one homogeneous block where everybody just sits inside a building. Each type of criminal will probably have a different kind of block associated to it. And this is very similar to how in SQL Server we have memory clerks. Now the memory clerk is fundamentally just like a cell block. What it means is that you have the buffer pool, which is a cell block that contains all the data pages. Then you've also got the optimizer cache, which is basically all the plan cache where all these stored procedures or the queries that you're writing, the execution plans of them are being saved. You also have a Sql Reservation, which is basically the stuff that is used for allocating memory, doing sorting and hashing, or basically group by and order by clause. So like that, XTP is another one which is used for in-memory OLTP. But fundamentally what you'll see is that different types of operations have different memory clerks, just like how different types of criminals will have different cell blocks. And the important thing to understand here is that there is memory pressure that happens to SQL Server, and that is usually adjusted by something called clock hands. And the clock hand basically has two types. There is internal memory pressure and there is external clock hand, memory pressure. So external memory pressure would typically be stuff like the operating system telling SQL Server, you need to cut down the volume of memory you're using because I need that memory for something else. That would be equivalent to basically like reducing the size of the prison so that the land around the prison can be used for something else. On the other hand, we also have internal memory pressure, which is basically where the internal clock hands come into picture. In an internal clock hand, what will happen is that, as you can see here, we have one chunk of the block, which is the huge one that we have here, which we'll call the buffer pool. Correct, and we might have another smaller block over here, which might be the optimizer or the plan cache or the Sql Reservation or any other XTP. Maybe this could be XTP. Correct. So let's assume that this is in-memory OLTP table, the memory used for in-memory OLTP tables, and this is the buffer pool that we have over here. Now, fundamentally, the buffer pool is usually the biggest consumer of memory, but let's assume that slowly we start inserting more and more data into the in-memory OLTP table. And as we do that, the in-memory OLTP table will request its clerk internally to expand the amount of memory that's allocated to it so that it can store more information. And that's basically when this particular block over here will start encroaching into the buffer pool. And as it does that, this boundary wall, let's assume that this boundary wall starts getting allocated over here. And now this block over here that we see would probably be what would be allocated to the in-memory OLTP, and it's actually taken away from the memory that would be allocated to the buffer pool. So this way what's happening is that SQL Server internally tries to balance out and resize the size of memory allocated to different memory clerks internally, and that's what that internal clock hand is about. So the external clock hand is always monitoring to see total usage memory consumption by SQL Server to release memory back to the operating system. And the internal clock hands are used to resize the amount of memory allocated to individual memory clerks. And between both of these, they go ahead and do a fairly good job of dynamically managing SQL Server memory pressure. The process of the internal clock hand and the external clock hand adjusting the memory is basically what we call working set trim, where SQL Server is ideally trying to identify a perfect balance so that it's trimming the amount of memory it needs to do the job without impacting the performance of the query itself, but at the same time fulfilling the needs of the operating system. So again, this is not a perfect example. There's a lot of generalization going on over here with this example, but I'm trying to explain to you fundamentally how the memory clerks work. So each operation, or not each operation, but typically what you'll find is that each aspect of SQL Server will have some amount of memory allocated to it via a memory clerk. A lot of the time what people use is an accountant or some kind of concierge service where the memory clerk is kind of requesting and then allocating memory and keeping it. I find the prison example works a lot better because it's easier to understand. Essentially what's happening here is that the buffer pool is where you'll find the majority of the criminals who are inside for some minor crimes and all that. And you might have occasionally certain smaller variations of criminals who are in for maybe a very serious crime, and that doesn't happen as frequently as a buffer pool, so they have a smaller allocation of memory. As the volume of data increases, we go ahead and resize the size of the buffer pool. So just like as the volume of crime increases, maybe crime is a seasonal thing, and maybe summers see more crimes than winters or something like that. In those scenarios, what you'll see is that we go ahead and reduce the size and increase the size of the memory cache. It could be simply a matter of suddenly we find there are a lot more female prisoners than male prisoners, and rather than build an additional block, they might just demarcate a portion of the cell block that belongs to males and reassign it to the females, and therefore internally resize the memory clerks so that everybody gets a sufficient amount of RAM to do their job. So this basic example is what I wanted to try and explain to you about how the memory clerks work. Now what we're going to do is going to see an example of that. Now, the Power BI report I'm going to show you is basically something I've just quickly put together by running a few SQL queries against the DMVs. And I will be explaining the DMVs in much more detail as we progress through the series. So don't worry about the actual DMV itself. Just try to follow the numbers and the state of the data as we run queries. Now, there's a lot of other information on this report that I don't need you to worry about for the moment. And so what I'm going to be focusing about mainly is just this portion on the right-hand side. Let me give you a quick breakup of what the data is. So as you can see here, the server was started a few minutes back, and you'll see that log pages and memory is enabled, and you'll see that my commit size is basically the amount of memory that SQL Server is willing to consume. We've talked about this in a previous video when we were describing the difference between the total server memory and the target server memory performance counters. You'll also see that I've got my max memory configured right now to 2048, so that's 2 gigabytes. Let me just go ahead and quickly show you that. So you can see that again, I've got my min memory set to 0 and the max memory set to 2048. And what you're seeing here basically is that I've got the server running in a very steady state. It's just been restarted. There's nothing inside it. So you'll see that out of the 2 gigabytes that I could potentially use, I'm only using about 500 MB at the moment. And in that 500 MB, I'm using only about 367 MB for the buffer, for the memory clerks, right? And the memory clerks are basically all the stuff that's falling under the min memory max memory setting. And in addition to that, you'll also see inside the buffer pool, I have the breakup over here, as you can see. So I've got my buffer pool, which is about 57% of the total consumption that's available at this moment. Correct. So that's what we have. I also have this particular table here which it explains the database and the number of pages from that database that's currently residing in the RAM. So you'll see that I've got a database called Airline, and it's got about 15,000 pages in the RAM at the moment. So these are things you want to pay attention to for this particular video. You don't need to worry about all these things over here. They'll be relevant later on. But let's go ahead and run this. So I've got a query here. As you can see, it's going to query a table called Airline Data Warehouse. And I've got a where condition which I've commented out for the moment. The reason I've done that is because this particular table, if you look at it, it's about 9 gigabytes in size. And what that means is that the table is so huge that if I did select star on this table, it's easily going to be more than what memory I have available. So if I do a select star on this table, it's still not going to fit inside the memory. And that's basically what I want to try and show you here. I've also, as you can see, I've got a group by statement. And in fact, let me just get rid of this. I've got a group by statement and an order by statement as well. So let me run this real quick. Give it a second, and what we're going to do is I'll just go ahead and copy this over to a new window and get it executed. So as soon as it starts executing, what you'll notice here is that you'll see that the size of this is going to increase. So I'm going to go ahead and refresh this Power BI report automatically, so I don't have to keep pressing the refresh button here. I'll just set it to refresh every 5 seconds. And as soon as it starts refreshing, you'll see that when the query ran, it started loading a whole lot of data from the disk into the memory. And what was earlier about 500 megabytes is now 207 MB. 2 gigabytes of commit memory. And in that 2 gigabytes of commit memory, 1.8 gigabyte is the buffer pool. And as you can see here, the buffer pool is using about 85% of the buffer pool is using 85% of the total memory allocation. And in that, you'll see that I've got my airlines database, and my airlines database, you can see that slowly it's ramping up. You can see that it's loading more and more data into the tables and into the memory. And as a result, you can see that the memory consumption is increasing. Now, we're going to wait for a few minutes to see how this ramps up. So you'll see that I've got 2041 MB utilized already. So you'll see that my target memory and my total memory are pretty much on the same page at this point. And I've got about 1.87 GB. So you'll see that there's a certain portion of the memory that's not really allocated from the buffer pool. Right, so you can see that basically this doesn't necessarily mean the buffer pool itself. What this means is basically all the memory that's been allocated from the Sysdm memory clerks DMV. So if you sum up all the memory used by all the different memory clerks, they're using about 1.8 gigabytes. And in that 1.8 gigabytes, 85% of that is basically being used by the buffer pool at this moment. So that's what this particular amount that you see here is about, 1.6. Now this particular DMV is actually the Sysdmos buffer descriptors, and what you need to keep in mind with buffer descriptors is that it's not going to give you a perfect count of all the pages in the RAM, because again that would cause a lot of overhead on the memory itself. So it's only going to show you a count of pages that are actually not having any latch on it at the moment. So pages that it can read without having to wait, those are the pages that it's counting. So there might be a bit of a variation between what you see here and the actual number of pages, but it shouldn't be too much typically, unless you have like a very large insert DML kind of operation happening and there's a lot of dirty pages inside the page, inside the memory, which are being latched at the moment. But what you can see here is that when this query is being executed, a significant portion of the memory is being allocated to this particular DMV, to this buffer pool memory clerk at this moment. And you'll see how quickly that ramped up from 500 MB to 2030 MB. Now, to kind of drive home this point, what I'm going to do is I'm going to go ahead and you'll see that it never really exceeds beyond 1.6. And the reason for that is because there are some internal limits set inside all the memory clerks. So the memory clerks don't just keep sacrificing their memory to the buffer pool. So as you can see here, the memory clerks are actually releasing the memory to the buffer pool. So that's where the internal clock hand comes into picture. The buffer pool needs more memory and they keep surrendering their RAM, but there is still a limit at which they decide that I'm not going to be able to give you any more. And then they kind of find a balance, and that's what we're seeing here. You will see that 1.6 GB is pretty much where it stopped, and we know that the table is actually much larger than that. So what you're going to see now is a lot of kind of paging activity happening, where the memory is being put into the RAM, fetched out of the RAM, and physical IO keeps happening as and when needed. And that's what this particular process is about. The important thing to understand here is that we still don't have an out of memory exception, and the reason is because internally SQL Server is trying to find out a just-in-time memory allocation kind of method where the query gets the memory it needs just in time. So the queries tend to be a little bit slower, but at least they don't crash just because they don't have the memory available, and that's what you're seeing here. Now let's see what would happen if we tried to introduce some other components and introduce more stress into the system. In order to do this, what I'm going to do is I'm going to go ahead and take this table that I have here. Right, so I've got all this data that I have, and I'm just going to go ahead and try and convert one of these into an in-memory OLTP table. It's not going to be pretty. It's obviously going to be a bit of a problem, but what I'll do is let me just go ahead and take this guy, paragraphs. Great, so I've got this in-memory OLTP table right now. I've got the original table called aircrafts_old, and I've got aircrafts. And for demonstration purposes, what I'm going to do is I'm just going to go ahead and say insert into aircrafts, select star from aircraft. Okay, so I've got an identity column there, so let me just get rid of that. There we go. All right. Okay. I forgot to populate the table, so that's why I have that issue. The table doesn't have any data. Now it's got some data, so it should be fine. Right. So as you can see, every time I run this, it's doubling the amount of data in it. So I'm going to go ahead and do this as, I'll just put it as 5 for the time being. And what you'll notice is that as I load it, you can see that immediately the in-memory OLTP has now encroached, and where we had the buffer pool earlier at about 80%, you'll see that now the buffer pool and the in-memory OLTP are roughly equal size. And that's kind of the point that I was trying to make earlier when we were talking about the jail example. And you can see as the in-memory OLTP table increases more and more data, you'll see how it's completely eaten up all the memory that was available to the buffer pool. And this is one of the big reasons why we say when you use in-memory OLTP, you want to go ahead and make sure that resource governor is enabled to throttle and prevent the in-memory OLTP from going into a runaway kind of situation where it just eats up all the memory available to the remaining clerks. As you can see here, you can see as I ran that, what's happened is that the buffer descriptors obviously don't store the data that was part of the in-memory OLTP. Those are the proper 8 kilobyte data pages that are stored in the buffer descriptor or in the buffer pool. Basically, in-memory OLTP is actually not the buffer pool, it's its own memory clerk, and so the data that belongs to in-memory OLTP, as you can see here, is now residing in its own clerk, and which has now suddenly become the biggest memory consumer in our SQL Server instance. So this is kind of the basic thing that I wanted to try and show you in this particular video about how the memory clerks go ahead and internally negotiate how much memory they need from each other, and they all cooperate and try to dynamically adjust the memory allocation using the internal and the external clock hands, and how all of that plays a role. Because what you have is that you've got that upper limits of the min memory, max memory over here, you got the commit size, you got the buffer pool. So you can see that the buffer pool is now not 1.8 gigabytes as it was before, it's now 943, and a large chunk of the memory is now actually allocated to the in-memory OLTP. So these kind of things are the stuff that you want to keep in mind. I did want to go ahead and mention about the difference. So if you look over here, what you'll see is that we have some kind of gap between what would be considered the buffer pool memory and the total limit. So we'll get into that in a future discussion. And also you'll see that always what happens is that the page memory usage in MB actually is lower than what would be the commit size or the buffer pool memory size, except when you enable buffer pool extensions, which we're going to talk about in the next video. So I hope you've enjoyed this video. I hope you're starting to get a little bit more of an appreciation about how all the memory clerks inside SQL Server cooperate with each other to improve the memory utilization of SQL Server without actually causing a system crash. And I hope that this video has been helpful. Let's move on to the next video and talk more in detail about the buffer pool extension and the role that it plays in granting SQL Server memory without actually granting SQL Server memory. And we'll also talk about some of these clerks in a bit more detail. I hope you've enjoyed this video, and thank you for watching. These videos take a lot of effort, and they actually take a lot of time more than anything else. So I would really appreciate it if you've enjoyed this video, that you consider subscribing and sharing this with your colleagues and friends. And thank you. If you like it, please do like and subscribe, and feel free to share it with your friends.